Delighted to have a wonderful speaker today on a very interesting topic. So I'm pleased to introduce to you Dr. Aleksandra Gasecka. She's based in two centres, the Medical University of Warsaw in Poland, and also the Amsterdam University Medical Centre, or AMC Centre in the Netherlands, where there is a very renowned Vesicle research group led by Rink Newland and colleagues. The research talk today is particularly of relevance, talking about calibrated flow cytometry and its ability to measure the concentration of extracellular vesicles in patients with myocardial infarction. Now, I gather Aleksandra just passed her PhD a few weeks ago with a cum laude distinction, which is absolutely fantastic. So congratulations, Aleksandra. And I believe, looking at your CV, you are going to work in the National Institutes of Health later this year. Is that correct? In October?
Yes, thank you a lot, Paul, for this nice introduction. I was going to go to NIH already last month, but due to COVID, that had to be postponed. But I very much hope to go there later on this year.
That sounds really great. Before we go ahead, let me quickly remind everybody that this is like a bi-weekly series for everyone who is interested in EV flow cytometry. You will find more information on our website, as you see on this slide, and you can especially, it's recommended to join our Slack workspace, where you can, during the webinar and also afterwards, ask questions, discuss, get help for anything you want. But for now, it's important that you head over to the Slack channel whenever you want to ask questions and use the channel seminar questions. And then at the end of the webinar, we will follow up the questions live, and those questions that couldn't be answered live will be followed up separately also after the webinar. That's important to know, I guess. So I'm very much looking forward to this talk, and thanks for joining us, Aleksandra.
Thank you. So I think I may start. So welcome everybody. It's an honor to talk to you today, and thank you a lot for this invitation. As Paul already said, I am a cardiologist in training and a postdoc at the Medical University of Warsaw, working in collaboration with Amsterdam University Medical Center. And today it's a great pleasure for me to talk about the calibrated flow cytometry to measure the concentration of extracellular vesicles in patients with myocardial infarction. So during my presentation, I will talk about extracellular vesicles as new potential biomarker of acute myocardial infarction. I will show you our study design and flow cytometry methods. I will briefly summarize the results and lessons which we have learned, and I will finish with a take-home message. So according to the total number of PubMed records, which is showed here on the vertical axis, most researchers in the EV field focus on cancer. And I guess this is also the case for my audience today. However, most people worldwide die from cardiovascular disease, such as acute myocardial infarction. The gold diagnostic standard for AMI is cardiac troponin. However, troponin is unspecific for AMI, since it is elevated also in other diseases, such as pulmonary embolism, chronic kidney disease, or stroke. Hence, a novel and more specific biomarkers are needed to predict, diagnose, and monitor AMI treatment. So, elevated concentrations of extracellular vesicles in plasma of patients with AMI were found in many studies. However, none of these results were hitherto translated to the clinic, so that at present there is no biomarker for AMI based on EVs in cardiology. And therefore, the goal of our study was to develop an EV-based biomarker to predict, diagnose, and monitor AMI treatment. Moving on to our study design, we performed a randomized controlled trial, EFFECT-EFE, where 60 patients with first acute myocardial infarction were randomized to antiplatelet drugs, to one of the two antiplatelet drugs, which are commonly used after AMI, clopidogrel or ticagrelor. Additionally, 30 healthy age and gender matched individuals were included in the study. Blood samples were collected at 24 hours, 72 hours, and 6 months after AMI, and EFs were detected with flow cytometry. The samples were collected in Warsaw and transported on dry ice to Amsterdam. So, moving on to our flow cytometry methods. To measure concentrations of EFs in our samples in a reliable way, we needed to determine the required dilution before staining and pre-dilute our samples. We needed to think about the calibration of our instruments, so about calibration of scatter, flow rate, and fluorescence. We needed to perform the necessary controls. And last but not least, we had to think about the efficient way of data processing of over 1,000 measurements done for this study. So we started with determining the total particle concentration in our sample. And to do so, we measured all plasma samples unstained and 2,000-fold diluted for 30 seconds. And these were also our unstained controls. And here on the left, you can see the number of samples on the vertical axis versus the total particle concentrations on the horizontal axis. And you can see that there is more than 100-fold difference in the total particle concentration, which we detected with flow cytometry. So both EFs, microns, and all other particles which were present in the sample. And therefore, samples required different dilution. Because if we dilute all our samples 2,000-fold for EV measurement, in sample with low counts, which you can see here on the left, we may risk having too low EV counts for analysis. And on the other hand, in samples with high total particle concentration, we risk swarm detection. What is swarm detection? Well, that's a phenomenon which is caused by the discrepancy in volume between the laser beam and the EV size particles. And for example, for Vesicle, at the concentration of 10 to the 10th particles per milliliter, more than 800 particles are simultaneously present in the laser beam, and they are perceived by the flow cytometer as a single event. And therefore, we needed to determine the maximum count rate to avoid swarm detection. So to do so, we did a serial dilution of pooled plasma samples from 10 male and 10 female volunteers. And here on the left side, you can see the concentration on the vertical axis versus the dilution on the horizontal axis. And we expected the linear relationship between them, as shown by this black line. So in other words, if you dilute 10-fold more, you expect to have 10-fold lower concentration of EVs. And we saw that this was true up to about 7,500 counts per second, as shown by this black point here. However, above this count rate or with the lower dilutions, we showed that the concentration which we measured deviated from this predicted line, which is a sign of swarm. And to determine the minimal count rate, we measured the background count of our instrument, which was also our buffer-only control. We measured it based on the buffer, and that resulted in 10 to 20 counts per second. And as you can see, if the counts were lower than this count rate, again, the measured concentrations of EVs were entirely not reliable, as you can see on this gray background here. And as a double check, we confirmed this by calculating the relationship between the median scatter and median fluorescence and dilution, which you can see here on the right, and which should be also constant. So you can see that in the swarm detection region, this relationship is not constant anymore, and the same in the too low count region, this is not constant, suggesting that the measured concentrations would also be not reliable. So altogether, we decided to dilute all our samples to about 5,000 events per second to be on the safe side. And this approach resulted in 7 different pre-dilutions prior to staining. And as you can see, they differed from 10-fold, which was the most frequent dilution, up to 400-fold. And the staining procedure added another 10-fold dilution, which was also taken into account when measuring the concentration. And moving on to calibration. Well, calibration is not easy in any field, as reflected by the recent developments in smartphone cables. And to start with, and as a reminder, calibration relates arbitrary units to comparable standardized units. So for example, scatter in arbitrary units to EV diameters in nanometers. And on the contrary, running daily beats is a quality control, rather to set up your instrument, to check the reproducibility of your measurements, but not a calibration. And that has already been discussed by Edwin van der Pol 2 weeks ago. So to relate forward and side scatter to diameter and refractive index, we used FlowSR. And please note that by using FlowSR, we were able to label-free differentiate between EVs, which are here shown in the lower part, and calomicrons, which are shown in the upper part. And we could specifically gate our EVs for further analysis. And here you can see an application of FlowSR. On the left, you can see the sample with high calomicron concentration, and on the right with low calomicron concentration. And since we know that the antibodies may aspecifically bind to calomicrons, which are changing the determined EV concentrations, FlowSR allowed us to increase the reliability of our analysis. Further, we calibrated flow rate, and that was done using beads of known concentration. And here on the vertical axis, you can see the flow rate, and on the horizontal axis, the experimental dates. So the adjusted flow rate is shown here by this dashed line, and the median measured flow rate of our instrument is shown by the dotted line. And as you can see, the median flow rate was very close to the adjusted flow rate, so within 10% on all experimental days, except for 30th December. So on that day, the instrument was not used for a week, and the flow rate measurement was done as the first measurement. However, since other measurements made on that day using other beads, so for example apogee beads, were fine, and on both experimental days closest to that date, which are shown here by the white bars, the flow rate was also correct. We interpreted this deviation on the 30th December as an artifact, and we assumed the same flow rate for all measurements. And finally, we calibrated fluorescence using MESF calibration beads by referring the median fluorescence in arbitrary units, which is shown here on the horizontal axis, to the fluorescence in MESF, which is shown on the vertical axis. Here you can see an example of fluorescence calibration for FITSI. However, we did the same calibration also for PE and APC, so for the all fluorophores used in our study. Now, moving on to the controls. So I discussed unstained sample and buffer only already when determining the optimal dilutions. So now I will focus on the isotype controls and antibody in buffer. Here on the left, you can see an example of isotype control, which shows that there was no binding to Fc receptors in this sample. We see hardly any counts here on the right from the red line. However, here on the right side, you can see an example of another control antibody in buffer. And you can see that despite high-speed centrifugation, which we perform in our lab to get rid of antibody and fluorochrome aggregates, you can see that these aggregates are still present in our sample. However, because these aggregates were not in the gate of EVs, we could gate them out, so get rid of these aggregates prior to our concentration analysis. So, as I mentioned before, the calibrated units enabled us to recognize different populations of EVs, so that we can see here. And here in the red circles, you can see populations of residual platelets and antibody and fluorophore aggregates, which could be gated out for EV analysis. However, still, of course, there was a problem how to differentiate between EVs, so our particles of interest showed here on the right side of the red line, from the background noise from the instrument, which is showed here on the left side. Well, so this was done in our study automatically. And here on the right side, you can see a histogram of the APC fluorescence of the data from the left graph. And to determine the gate, the software took into account all data points which were right from the peak and down to 35% of the peak height. It fitted them with a linear function, which here has a strange shape because it's a log scale. And it set the gate 1.7 times above the intercept with the horizontal axis. So here that is showed with this, the auto gate is showed here with this red arrow. Okay, so with this we calibrated our machine, so we could be already happy. However, to calculate the reliable concentrations of EVs, except for calibrating our machine, we also needed to monitor and correct for potential count rate variations. These variations could be caused by flow variations or by air bubbles, difficult to say. However, here you can see an example how important these variations are. And on the horizontal axis, you can see the counts. And on the vertical axis, the time, which is up to 120 seconds. In our study, we measured all samples up to 120 seconds. And the orange bars show the seconds, the time periods, where we excluded, which we excluded from our final measurement because the median count rate deviated more than 25% from the mean. And for example, here at the end, you can see a huge increase in the count rate, which is definitely not reliable. But still, somebody could ask, yeah, okay, that this can happen with flow cytometers, but does it really matter for the final result? Well, based on this example, I hope to convince you that it does matter. So here you can see a comparison of two scatter versus fluorescence plots before time gating on the left and after time gating on the right. And you can see that this pretty big cloud showed by the black arrow disappears after time gating. So this was an artifact caused by unstable count rate in our flow cytometer. Okay, so finally, after we calibrated our flow cytometer, corrected for count rate deviations, removed residual platelets and aggregates, applied flow SR, and determined fluorescence gates, here you can see an example of the final gate for CD61, positive EVs on the left and lactathirin positive EVs on the right. And you can see what was pretty promising and made us happy, that most of the EVs, the majority of them, had a refractive index of below 1.4, which is in accordance with the current knowledge about the EV refractive index. Well, so you can imagine that all these steps would be very challenging and very time consuming for a person with a medical background like me. But luckily, in our study, all calibration steps and data processing, including FlowSR, were performed by an automated software which was developed for this study. And this software is now currently further tested in our lab. Well, that brings me to the results. Here on the vertical axis, you can see the concentrations of EVs, and on the horizontal axis, the different time points in patients who were treated with ticagrelor and clopidogrel. So at the beginning, all patients received clopidogrel, and then they switched. And you can see that in patients treated with clopidogrel, the concentrations of EVs increased. The same actually for ticagrelor, from 24 hours to 6 months. However, this increase was less on ticagrelor. So you can see that there are differences between antiplatelet drugs in terms of platelet EVs. Other results are included in the JTH paper, which was just published. So if you are interested in it, please read them. However, the most important flow cytometry message here is that these significant results were found with a fully calibrated assay. So now I hope that it is possible that somebody of you can reproduce these results in your lab. Okay, so I think what is more interesting from the flow cytometry point of view are not the clinical results, but actually the lessons which we have learned during this study. And here I would like to share with you my adventure from the beginning of my PhD. And then I had a pretty old centrifuge to prepare plasma, but it was still kind of fine. And it was impossible to disable the brake on this centrifuge. Well, you could expect that if you have your centrifuge brake on, you will see, of course, less clear boundary between red blood cells, between the buffy coat of platelet and leukocytes, and between your plasma. However, does this really matter? Well, it does. So here you can see a comparison of a plasma sample prepared with the centrifuge brake on in the panel A. So you can see a huge cloud of residual platelets, and without a brake in panel B, where most of these platelets are entirely gone. So the first lesson which we have learned was actually to turn off our centrifuge brake. Do residual platelets matter? Well, as you can see here, on the vertical axis, the concentrations of platelet EVs are shown in brown, and concentrations of erythrocyte EVs in green. And on the horizontal axis, there is a concentration of residual platelets. So we have seen a strong correlation between platelet EVs and residual platelets, and we hypothesized that due to freezing, residual platelets actually may fall apart into EV-sized particles. On the other hand, it could be said that maybe the donors with high platelet count have more residual platelets and subsequently more platelet EVs. So the right graph shows the concentrations of platelet EVs in black and residual platelets in red versus total platelet concentrations in our patients. And you can see that this correlation is much weaker. Hence, because we don't really know the reason of the such strong correlation between platelet EVs and residual platelet concentrations, it is crucial to report the concentration of residual platelets in your sample. And that has already been recommended in a roadmap for blood EV published in JEF in 2019. The next lesson we have learned is that plasma require custom dilutions, as showed on the graph on the left, and as I already discussed previously. But actually, why is this the case? So why do the total particle concentrations in plasma differ so much? Well, the FlowSR allowed us to determine the concentration of calomicrons, and therefore we could investigate the relative contribution of particles to the total concentration. And here on the right side, on the vertical axis, you can see concentration of particle fraction, and on the horizontal axis, the total particle concentration. And you can see that the leukocytes showed here in red differ only one order in magnitude, whereas chylomicrons, which are showed here in black, differ range actually from 10 to the 7th to over 10 to the 10th particles per milliliter. And that actually shows us that the total concentration of particles in the sample is actually determined by chylomicrons. And from a clinical point of view, this is very important when developing EV-based biomarker, because it seems crucial either to draw blood from fasting patients or at least to be able to identify chylomicrons. And another lesson, last but not least, was that the final result depends on small details, such as centrifuge break, which I already told you before. Without reporting these details, it is impossible to reproduce the results, even if we calibrate our instruments perfectly. So on this slide, which I'm not going to read, but I just wanted to show you examples of things which you should report, and this has already been summarized in MySEF criteria and in the recently published MiFlowSeed EV. And the last lesson, which I would like to share with you, was that the quality control actually helps to interpret the results. So, for example, in our study, we measured the temperature every day. So here you can see a plot showing residual platelet concentrations on the vertical axis versus a date on the horizontal axis. The residual platelet concentration was pretty high in our study, except for a few days, which are shown here on the orange background with these red dots. So why could it be the case that on some days we found relatively low residual platelet counts and they were pretty clustered? Okay, so when we analyzed the temperature on that day, it turned out that the maximum temperature measured in the centrifuge room was more than 26 degrees, since apparently here in April and in August or July, we had a pretty hot period in Poland, no, in April, maybe due to global warming. Nevertheless, thanks to this, we could exclude the samples with low residual platelet counts from our study due to a reason. And that brings me to the take-home message. So the three most important take-home messages are to calibrate your instrument, so to relate arbitrary units to comparable units, as I have showed you with all the flow cytometry plots in this presentation, to implement quality controls, so for example to measure temperature, because it may help you to explain some deviations in your, for example, residual platelet counts, and even more important, to measure the residual platelet concentration in your samples, and to report it all according to MySEF criteria and MiFlowSeed EVs. And at the very end, as a medical doctor, I think that the calibrated flow cytometry is a huge breakthrough, because it allows us to go from single-center studies to multi-center clinical trials to develop EV-based biomarkers so that we could compare comparable things. And with this, I would like to acknowledge my colleagues from Amsterdam University Medical Center, from Medical University of Warsaw, University of Helsinki, and University of Birmingham. And I would like to thank you all for your attention.
Thank you very much for the presentation. I really enjoyed it, and a lot of fascinating data, which I'm sure has created a lot of interest on the questions, which we're going to go through in a moment. I've got a question to kick off with. You showed really nice resolution of your vesicles from chylomicrons. If you did a fasting sample, did you still see chylomicrons, and was it still a significant problem? Or would you recommend fasting as an approach to eliminate the chylomicrons?
So I would like to go back to that slide, because actually I have an example of that. Here. So here on the right side, you can see the low chylomicron concentrations, and this was the sample collected from a fasting patient. And by fasting, we mean more than 6 hours of not eating and not drinking anything else that, for example, water. So nothing sweet. And as you see, we still see some chylomicrons, but they are much less than here when the sample was collected right after the patient was eating. So this is the direct comparison.
Okay. So you think in a fasting situation, if you know we standardize, if we were going to do a study and do fasting samples, we still need to eliminate these residual chylomicrons from analysis, ideally.
I think ideally that would be the best, because since we know that they may specifically bind also to the antibodies, I'm afraid that if we don't eliminate them, this may still result in, well, not very reliable EV concentrations. But if we don't, if we have no option to eliminate them, I think definitely we should collect plasma samples from fasting patients, because as you can see here on the left, the chylomicrons definitely determine the total particle count in the sample.
Yeah, also thanks a lot for the great presentation from my side. We have some questions in the Slack channel. Let's start with which software did you use for the autogating or the automatic threshold determination? I think you mentioned that later. So is this software freely available? Is it compatible with all different flow cytometers? Is it commercially available? Can you tell a bit more about this?
Yes, absolutely. So this software was developed actually during data analysis for the study, and due to the fact that we had this huge amount of measurements to analyze, and so it was developed a few months ago. So at the moment it is still being tested in our lab, and it is not yet commercially available. However, as far as I know, it is becoming available or being tested on more flow cytometers than just Apogee. So I think in the future it would be possible to use it also in different labs.
We have quite a few questions on the channel, so we'll open up with Joanne asks, what were the sizes of the beads that you use for the MESF calibration?
Okay, so about the MESF calibration, as you can see, that these were 2 micrometer beads, for example, for APC, but you had to, so we had to order them. They are commercially available from BD, but we had to make like a custom request, because they are not mentioned as products of BD on their website. But if you write an email to them and ask about these beads, it should be possible to get them, just to buy them.
Yes, there are more questions. So what's the rationale of looking at CD61 only and not include CD41A or CD62P markers? And related to this, maybe a bit, why do you still detect residual platelets? So how do you control for disrupted platelets that can lead to increase in CD61 positive EVs? I find that question quite interesting. I was about to ask something similar, because I think it also depends on processing a bit, right? So how you process the sample, can you avoid that platelets somehow disrupt and create smaller EV-like particles or something like that?
Yeah, absolutely. Thank you a lot for this question. So here I only had a chance to or to show you one example of the results, but we measured many more markers of platelets, also of leukocyte, of endothelial cells, erythrocytes, and also of EVs exposing fibrinogen and lactatherin. And these results were compatible with the results showed here, and they are presented in JTH in details. So I agree that measuring just CD61 without including P-selectin is not that is not really measuring EVs from activated platelets, so we also included it. And about this count of residual platelets, well, so as I said at the beginning, in our centrifuge, despite using the what we call Lacroix protocol, so the double centrifugation, which is according to also recent circulation research guidelines, we still found relatively high concentration of residual platelets. And of course, it was not possible to exclude that they may have ruptured, as I said, to EV-sized particles. But this was the reason why we excluded from our analysis the samples with relatively low residual platelet counts to make sure that at least we have the same residual platelet counts, although it's pretty high, for all samples. And since the study was randomized, so it might have caused some kind of systemic error, but at least it was the same for all samples. But definitely I agree that, well, it's important to report it. And of course, gating them out does not mean that this was the platelet count which we froze, but it can be that some of them ruptured into EV-sized particles.
Okay, so we have some more questions. So the question from Ganesh says, thanks for the talk. Which parameter do you use to say the dilution in terms of the swarm versus non-swarm detection? Mm-hmm. That's the question. I mean, it might be slightly confusing, but...
Mm-hmm. Well, so as I explained here at the beginning, I would like to go back to this slide. Sorry for that. Oh yeah, here. So actually, we at the beginning we decided to dilute all samples 2000-fold, which is a huge dilution. So the parameter we used was just count rate per second, and with this 2000-fold dilution, we then made sure that all samples were actually below 5,000 per second, and the 5,000 per second parameter was already explained here. So this kind of swarm boundary, this black point, was 7,500, and we decided to put the swarm boundary a bit lower to make sure, as I said, that we are on the safe side, that we do not exceed the swarm threshold. And to have this statistically meaningful counts of EVs, we wanted to dilute all samples to more or less 5,000 events. But of course, for some samples it was 4,000, for some it was 3,000, but still it never exceeded this swarm rate, and it was always meaningful enough in terms of different EVs to draw some statistically significant conclusions. So the parameter, I don't know whether I asked the question, was just the count rate per second determined here due to this 2000-fold dilution.
Okay, that's a very helpful answer. So when you run a typical sample, how long does it take you to run that sample?
From freeze-thawing, I mean, to maybe getting the result.
Just the flow analysis, where you're obviously optimizing the concentration. So how long does it take you once you've got the sample, you're sending in front of the cytometer, how long does it take you to optimize the dilution to the count?
So we had a few aliquots of the sample from the same patient, and this plasma was mixed prior to freezing the aliquots to make sure that the concentration is the same in all aliquots. So for example, for the samples here, they were all diluted 2000-fold at the beginning, and then based on the event count with 2000-fold dilution, we determined the required count as we showed here, so that the final dilution in kind of clusters. So we decided for 7 pre-dilutions. So, well, it took us kind of, I would say, 2 days. So on one day we determined all event counts with the 2000-fold dilution, And on the second day, and that was already the day of the analysis, we diluted the samples based on the calculated pre-dilution, as I show here. And if, again, I think there were a few samples where this dilution was incorrect or exceeded 5,000 counts per second, then we did it again. But we had to repeat it only for a few of these over 1,000 samples. So that was a pretty efficient procedure. I think more efficient than calculating or measuring the pre-dilution at the same day as doing the measurement, I think.
Okay.
So the next question is coming from Ring Newland. He's wondering why the concentration of platelet EVs is so low. He says that your platelet EV concentrations are 1E6 per ml. Platelets have a concentration of 1E5 per microliter. Can you comment a bit on this? I guess it was covered a bit, but maybe good to emphasize.
That's true. So generally here on this graph, the double positive events are showed. So both CD61 and p-selectin positive. So if we looked at the single positive event, this was higher, so about 1 magnitude order higher, so about 10 to the 8. However, I think the low count resulted from gating out all the artifacts. So we gated out, as I said, chylomicrons, we gated out residual platelets, we gated out antibody and fluorochrome aggregates. So, well, it might be that higher concentrations of EVs measured in some studies are due to gating all these events together and perceiving them as EVs. However, that also, of course, depends on the sensitivity of the flow cytometer, and on the protocol. But I think in our study, the low concentrations with relatively high sensitivity of flow cytometer of down to 200 nanometers for EVs resulted from gating out all these artifacts. Thank you, Ring, for this question.
There's a question from Desmond Pink. How do you improve throughput if you have to customize dilutions? Is this a realistic approach?
That's the only approach for clinical studies. Since, for example, when we did the lab experiments, we first determined the count rate. And on the same day, we performed the experiment. So we did the labeling and measurement. But in a clinical study, when you have a lot of samples to analyze, well, you have to kind of determine the optimal dilution to prevent what I said before, that the concentrations will be measured in a not reliable way, either due to swarm or due to count rate. And as I think said at the beginning, this procedure was pretty efficient, since one day we just measured on a few well plates the count rate in all samples just for 30 seconds, so that didn't take much time. And then based on this, we calculated the optimal dilution for each sample, which needed some calculations, but it was also pretty efficient. And that allowed us to dilute the sample directly to the optimal dilution when doing the real clinical measurement, so that we only kind of lost one alipot of a sample, like 200 microliter, and then for the next time the measurement could already be done. So I think that's a pretty efficient approach, and I hope it's realistic.
Okay, next question comes from Joanne. She's wondering if you controlled for diurnal variations.
Well, yes, so always blood was collected in the morning, and patients were always told to be fasting, but we could see based on chylomicrons that patients at 24 hours and 72 hours time points were indeed fasting, because I collected blood myself in the hospital before they had breakfast, so I knew it. Whereas at the time point of 6 months, we have seen in some patients much higher chylomicron concentrations, although the patients were told to be fasting. So we were even thinking of using FlowSR as a kind of check whether your patient is really or has really been fasting according to your instruction. This was done in the morning from all patients, so between 7 and 10.
Okay, thanks. I think we are coming to the end. I'm just wondering if you maybe can share, you already did this a bit, like in the section what you could learn from your experiences. How would you design the whole study if you could redo it with your experience now? Would you include more markers? Would you organize everything differently? I think that's kind of important when you look ahead, and also related a bit to how scalable it is, how many samples can you measure, like all these different questions. Would you have some thoughts about what you would do differently?
So that's absolutely great question, and well, I must admit that we learned really a lot from this study, and that I would design the next study absolutely different. But I think this is good, because as you can see, well, we did not end up with a biomarker based on this study, but we ended up with a lot of insights. And so first of all, I would always, as the question before already suggested, take blood from patients at the same time. Well, that was done in this study, but before collecting or including many patients, I would actually check the performance of a centrifuge, for example. So I would just collect plasma or prepare plasma with my protocol from a few patients, and I would send them for a quality check, so that you can see whether the residual platelet count is low, whether you can see EVs, whether there are no, I don't know, artifacts or strange phenomena in this sample, whether your centrifuge works properly, etc. So I would say this is very important. And well, from a clinical point of view, and because we have showed that antiplatelet drugs affect EVs, I would collect blood from patients at the emergency department and not after the intervention, when they already had received drugs before, because we can see that this will not help us to develop a biomarker, but this rather introduces another variable. So that's it. And well, I hope this software will also become broader available, because definitely I would use the software, since I think it's very important and crucial to gate out all the potential artifacts which could be, even if we have no residual platelets, due to count rate variations in the flow cytometer. So that I would definitely do again. So I hope we can implement all these improvements in a future study.
Thanks a lot for sharing your data and your thoughts with us today. Before wrapping up, I would like to encourage everybody who hasn't done that yet to join our Slack workspace, where you can ask questions. Also, if you should watch this video later on YouTube or somewhere else, or if you have questions that are unrelated to this. So that is supposed to be a discussion platform for everybody who's interested in EV flow cytometry. So everything is open. The next talk will be given by Josh in 2 weeks. Thanks a lot, Paul, for joining us today. Do you have any final remarks?
I think it was a really nice presentation. I think there's a lot of work to do still on standardization and flow cytometry, but I think this work is now beginning to reveal some interesting variables and also some interesting approaches that are beginning to solve the problem of EV measurements by flow cytometry. And I think it's very exciting. So it was a great presentation. Thank you.
Thank you a lot for your attention. And I'm also available to answer questions if somebody has any more, either on Slack or per email. So please don't hesitate to contact me if you have more questions.